I started with the experiment, which I had in the trailer for a while, and we had some very interesting results. And let us see what is going. Let's start. I am Jaco, and let's look at the behavior of electromagnetic wave on a transmission line, and I'm talking a power transmission line. Okay. The first experiment that I'm doing is I'm attaching my injection points on the one side of a transmission line. And the picture over there, you can see that I'm intending to use the red phase, which is on top, and the top one is of course the earth conductor. That's the earth wire. That happens to be 106 square millimeters conductor, aluminium. And then the main conductor is a 323 square millimeter aluminium Kingbird ACSR conductor. So that's the basis of the first experiment. Over here you can see I have got the approximate sizes relational to one another of the earth wire on top there. That is the 106 square millimeter aluminium ACSR, and then there's the Kingbird, 323 square millimeter aluminium. And then on the other side of the transmission line, there's a cable feeder that goes into this 33 kV panel, and the cable that is fed from there is a 500 square millimeter aluminium. So the intention is to inject on the main conductor, which is the second one from the top, and expecting the earth return via the top conductor, and of course a portion of that earth return is via the actual earth as well. Okay, so first of all we found that line, and we have to of course get to the conductor where we have to connect our injection point. We do that with a link stick and very carefully connect a fault-rated conductor using a very special clamp to the top conductor over there. You can see that. So thank you, Gert, for doing that for me. We've connected now. We're coming down with our conductor. Conductor was earthed at that point. At that point over there, I remove it and I connect it to the ascending end of my 12-volt battery and switch. I isolate it from the rocky ground there, so we don't have any short circuits over there, and then we're going to inject. So if I sketch that, you will see that I have done a schematic sketch over there, where you can see that the injection current is going via the 10-kilometer line first, then going into the short piece of aluminium cable. There's either a short circuit at that point there, or an open circuit, because you can of course also test it on an open and a closed circuit, and I have done both. So, and then it returns via the cable screens, and there's a separate bonding conductor as well, and then the 10 kilometers of overhead ground wire, and here's an indication of a portion of it returning via the real earth. Also, the DC current I have calculated to be 4.12 amp, and when I have a short circuit on the other side of the line. So you can see the circuit diagram over there, and the interesting part is I predicted 4.12 amps, and when I measured that, there are more detailed recordings coming, but this is just the first one. It indicates that the DC, the maximum DC current it builds up to is 4.2 amp measured, and that compares very favorably with the 4.12 amps that I've calculated. And the same thing, of course, at this point, we already know from the previous videos and the theory that this is not a smooth increase, exponential increase in charging that line. It, of course, is stepwise, and the reason that it's stepwise, we already know, is that the electromagnetic wave is bouncing back and forth, and it's increasing in steps. And the first step I have calculated to be 32.6 amps by calculating the characteristic resistance of this first transmission line that you enter into. That, of course, is the first step, can only be that. It has nothing to do with the second transmission line, which is the cable over here, and it has nothing to do with the short circuit that we have at the end here. So the first capacitive current there is expected to be 32.6, and I've measured that to be, in this particular case, 31 milliamps. So theory comes very close to the reality that I've measured over there. It's running through a line. It's on and off. The voltage is the green one, and the current is increasing every time the wave comes back from the other side of the line. This is the long time response that shows the buildup of the DC current over here. Builds up to the calculated figure of just over 4 amps. In the in the oscillogram below, I have opened the short circuit on the remote end of the line, and what you would expect possibly is a little bit of charging current, and then nothing, because it's an open circuit. But what you in fact get is an oscillation. So that oscillation is very interesting. We can look at that in a little bit more detail going forward. Yeah, but you actually see a waveform where you actually expected just nothing, a little bit of charging current. So let's go on more. So let's go to the next slide. This is a very complicated effect of what happens. Here I've placed the recording for a short circuit at the remote end on the above recording, directly above the recording for open circuit at the remote end of the line. So what's the difference? The first 64 microseconds are exactly the same, and you notice that because at that point when you're starting to inject a wave into the sending end of a transmission line, until it has have bounced back and you've received the reflection, you have no idea of what's happening on the other side. So whether that's open circuit or closed circuit, it's exactly the same thing. Therefore, you can see that these two waves right at the beginning are exactly the same, and that is because you have no foresight in what is at the end of the line until the wave returns. Now, how fast does that wave return? I calculated that. I've measured it on the oscilloscope, that this period here, which corresponds to going from the sending end to the remote end, back to the receiving end. So this is 2 lengths of overhead line. So that is done in 63.74 microseconds according to my recording over there. So let's calculate the speed of travel. It's 9,551 meters times 2, because we're going there and back, and we divide by the time it takes, and we divide by the speed of light just to get a percentage of the speed of light. So let's do that. You multiply it out, you get that divided by speed of light, and you get 0.996 c. Spot on. That's what I expected. That's the speed of light in air. I'm very happy to see that the speed of light hasn't changed since I've last studied it. The question is, what is happening here? We're having a pretty unusual, non-symmetrical wave running basically at the same periods as you would expect the back and forth wave, but something very strange. Now, this is the effect of the second piece of cable that is attached. So just a reminder, the first portion of that transmission line is a 9,500 meter overhead line, and then it connects to a 500 square millimeter aluminium 330 odd meter transmission line there. So you will see that what is actually quite strange here, if you look at the short-circuited situation, after that first stretch of input current into the transmission line before the reflection arrives back at the sending end, of course it's identical as just discussed. However, when the reflection comes, I'm seeing an addition going up there. I'm seeing the same thing over here, an addition going up, even though I have no short circuit on the other side. I have an open circuit on the other side, and I'm still seeing an increase in here instead of a decrease. So you are coming from a high impedance to a low impedance, and that low impedance approximates a short circuit. And what happens with a short circuit? We already know. This is what's happening with the short circuit. With the open circuit, we are supposed to have an edge going down here. But what's happening? We're seeing both. We're seeing first an edge going up, and then we have some strange way of coming down. Now, that can be explained by this diagram over here. You will find this indicates the first incoming wave from the sending end. This indicates the interface that I was talking about, this interface over here. And what's happening is, because it approximates a short circuit, even though there's an open circuit at the end, 330 meters further, there is an almost short circuit at that interface where the overhead line enters into the underground cable, and that causes it to behave like a short circuit. What's that? It means it comes in and it bounces. At least 90% of that wave bounces back. What does that mean? It means it gives me this edge going up. Okay, why is it being eaten away over there? Because at the first time when that incident wave into that interface arrives there, say 90% is reflected back, but 10% is transmitting across. But that is a very short piece of line. It's 300 meters. So that 300 meters, and it reflects on the other side. So when it reflects, it comes back, and when that portion is reflected and it comes back, it reflects again and again and again and again. That means every time it reflects, it imparts a part of that energy is coming back this way. So just using the same 90% that I used before, 10% would be coming back in bits and pieces. And it is a known interval between them, because it's the same distance between those, and every time it goes back and forth, that 90%, every time it goes, it imparts of 10% of the energy over there. And that you can see here. If you would have a method to actually zoom into that, we don't have a method there, you would actually see the stepwise bits over there, because those are the steps. Those are the little steps that are eating away of that pulse. If that hadn't been there, then of course it would have been just a short circuit, which would have gone over here. Okay. So that explains why we have some interference. It's this latter half of the cable of the transmission line that is interfering with the first half of the line. And since this is an interference, and I actually wanted to see these very, very academic and clear-cut signals, I decided to go to another overhead line where there was actually not a cable connected as yet. So it was an open overhead line, much shorter, unfortunately, but still, because there's no interference of cables, the length doesn't actually matter. I have I could change 9.5 kilometers overhead line which goes over to a 300 meters underground cable. I could remove that and I could use a different line that it has just over a kilometer of clean overhead line without any connections, without any interferences, without any interfaces in between. There is the earth, so the temporary earth, making sure that we're not going to collect too much static electricity from the lines, safety precaution. So I'm just showing where we are connected to. With this particular one, we're connected to the bottom conductor. And I'm also now showing you where the earth conductor is being tapped off, because that goes directly to the top of the line and the top conductor. Earth returns via that grey wire. And we will be injecting now. Again, on, off again, right? So what are we seeing? With a short circuit on the short line. The voltage is going up straight away, okay? And then the current is increasing. Okay, and that is the steps that we discussed at a different point. And now we do the same thing with the open circuit on the other side. Same test. And now we're expecting what? An oscillation? Yes, and we are seeing exactly that. So that's exactly what we receive, what we're receiving. When you close that switch, you have the wave traveling along the 1 kilometer line, gets to the short circuit, and it follows the short circuit and it comes back on the earth, which is essentially the wave just coming back at you. Every time it comes around, the battery is there, it collects more energy, and it actually forms this step function going up. When you close the switch in the open circuit, so the waves start traveling down this main conductor. It arrives on the other side. There's no path for it to come back, to return via a negative wave coming back. There's no way for it, so it returns on its from the end of that open conductor. So let me put those two waves on the same graph, and it's for interest's sake, I've done that. So look at that. It beautifully matches. So it goes back to the point where I said when the wave starts traveling out from the sending end, it reaches the far end in the middle of that first step, and it bounces back either on the lower conductor or on the higher conductor, whichever one, depends on whether it's a open or a short circuit, and it comes back, and at this point that has now reached the sending end. Now, whether it is on the top conductor or the bottom conductor will either give you a cancellation over there or an addition over there. So that's how these things are exactly the same wavelength, because it's exactly the same time delay. What time delay do we have? In this particular case, let's calculate the speed of travel again. So I've measured with my oscilloscope, I've measured this in a short line to be 7.8 microseconds, quite different from the 64 microseconds that we've had in the 10 kilometer line. So this is quite significantly shorter. So, and I do the same calculation. I've got 1,118 meters times 2, because it's to the far end and back, times 2, divide by the time and divide by c. So we do the same thing, we get 2.95 c. So in the end, what is the takeaway from this video? I think the slide that I have on at the moment there is very, very telling in the actual symmetry that we have between open circuited and closed circuited transmission lines. The fact that the first the fact that the first lot over there is identical. As you can see on the overlay, they are in fact identical. So what you have is the identical first step, which is the same amount of current that will flow into the space between the transmission lines, into the electromagnetic wave that starts at that point. The interaction between the capacitance and the inductance of the transmission line. So the immediate contribution over there, of course, and then at this point, which is the return point, that depending on whether the wave is on the same conductor coming back, in other words, an open circuit on the other side, over here will be a cancelling effect, and it cancels that one and starts a new wave on the other direction. And then of course the opposite, if you are sending, there is a short circuit on the other side which conducts the wave around and a negative wave back, then when that negative wave turns around again at the battery, it becomes a positive wave and it adds with more energy, and it starts the stepwise function, which incidentally has the exact timing as the open circuit one. So it very nicely shows the fact that there's a wave going there and back, and again there and back, and there and back, and either it builds or it cancels. So that's the interesting part. And of course we've seen that this recording shows that we have light speed in air. I have done another experiment, and that is asking yourself what will happen if you have a short circuit on the short transmission line, the 1 kilometer one. You have a short circuit, you're pumping energy in there, and then you're opening the circuit breaker. In other words, you're opening this switch. So let's look at what happens when we stop the current. That's a very interesting question. So, and why? Let us just recap quickly. We have a transmission line over here, which the combination of these two parallel lines is the transmission line. This transmission line comprises a capacitance between them and an inductance along those lines. So the inductance, I'm going to focus on the inductance at the moment, because once you have a DC current in that transmission line short-circuited to the at the far end, and a circulating current around here, you have now a constant current. It has now already built up along the curve that you've previously seen, all the steps, all the waves going back and forth. It has now stabilized. Normal Ohm's law is now applicable. We have calculated the current to be around 8 amps in this particular case due to the resistances that we have around here. So it is now a DC current and let's call it a permanent field. It's not permanent, but it's permanent while the DC is being constant. The the magnetic field around this cable, this top cable, the bottom cable over here, is now fixed. Nothing is happening in terms of traveling waves, because everything is settled. So the moment you open the switch, the current on some way, because you're removing the source, so the moment you open the switch, the current must fall from 8 amps DC to 0 amps DC. So there's a transition that is expected. How is that transition happening? We'll see what happens over there. So the magnetic field is fully charged, as much as it can be permanently charged for an 8 amp current through that single conductor, and a conductor coming back. So the magnetic field is stable, and the moment you stop it, and it starts falling to the current has to fall to 0. Therefore, the magnetic field is going to fall to 0 as well. It's going to start the moment the magnetic field changes, it's going to form an EMF along this loop, and it will have a positive end on this loop over here, at this point of the loop over here, and it will force a current through the circuit. So that EMF will force this current through the circuit. The losses through the real life losses that we have will force that current to reduce, and not keep indefinitely at the same value. So there are resistances there, and those are the sources of the losses. So let's have a look at what happens. Okay, there's my recording that we made. You see, first of all, you start with the 0 point of the red dot over there. It ends at zero as we expected, and it starts at 8 amps over there. 1, 2, 3, 4 divisions at 2 amps per division. That's 8 amps. Starts at 8 amps, and it decays to 0 amps. So at that very point, as I mentioned over here, as the current is moving through here anyway, and on DC, the moment you open the switch, the collapsing magnetic field will cause a positive on this side to appear, to change from the positive that's sitting here to a positive sitting here. How do we see that? Look at the green wave over here. We have a constant voltage being fed from the battery onto the transmission line. And the moment you open the switch, it shoots down to a negative value. It shoots down to, in fact, around about negative 60 volts. It looks like about 20 volts per division on that scale over there. That's 3 of them. That's around 65 volts change to about minus 60 volts. So from a 12 volt battery, I'm experiencing a minus 60 volts voltage level. That is normal. That is what happens when you allow magnetic fields to contract and cause EMFs. So it goes the opposite direction, minus 60, and the current starts dissipating. Question is, let's have a look at where that current is now. The current is going through here around the shunt resistance that we have here. There, through the shunt resistance. The shunt resistance is creating a voltage which we can measure, and that voltage is the red signal, and the signal is scaled as a current on my oscillograph over here. Okay, so that's where it's going. And let's follow the current on. It has to be a complete loop. So the current is coming there to my switch, but the switch is just opened. The switch has physically just opened. So how can this current still be flowing? After, at that very point, we can see that the switch is opened. You can see the swing in voltage. That means the switch has opened, but there is still current flowing. How can current flow if there is a switch that has physically opened? And that is because the moment you open this switch, these points of the switch are now a couple of millimeters apart, and there's a capacitance in between those. So what is happening is there's a buildup of electric charge. So what's happening is the current is pushing along over here. It's not stopping. It's pushing along. The switch is open, but it acts like a capacitance. It's like a dam. The dam is getting, so I'm pushing voltage into that capacitance. There's a voltage difference starting up between those 2 points, and that is because of the charges that are increasing on that point. This one point is becoming positively charged, and the other one is negatively charged. Of course, as usual, we are talking charge flow here, not electron flow. It's just a rider, but anyway, that's exactly how it is. So what happens after the magnetic field has collapsed? At this point over here, the magnetic field in my conductor has now collapsed. There is nothing happening anymore. What happens at that very point? There's no more force. There's no more EMF coming from this side out here. Okay, so what happens now? Now I have a charged portion of a circuit over there. So what happens is that charge now starts pushing the current again back in the opposite direction, because remember this was now positive. So now there's no more there's no more there's no more EMF coming from this inductive circuit over here. So there's a dam. What happens if there's no more current flow into a dam, into a pipeline, into a dam? It stands still. Then the pressure on this side is starting to cause the current to flow in a different direction. So what we have now all of a sudden is we have a oscillation starting to occur on this side because of the energy coming back. At the same time, and it's not, you have to remember, at the same time, while this transmission line it is not a pure inductor, it's also a distributed capacitor. So what's also happening is at the same time that it is emptying itself out from magnetic field, those magnetic fields, as this current is flowing, is charging up this line capacitance. So at the moment when the current flowing through here, decaying current, has emptied the magnetic field, the magnetic field is now fully collapsed. There is no more EMF driving a current out this way, and it just stops. And what happens if it stops? There's a dam here. There's a positive amount of charge over here, and what I haven't mentioned earlier on is this transmission line over here is a complex structure of capacitances because of the capacitances between the conductors over there and inductors, and it forms the transmission line. And what's happening is, as this thing is emptying out the magnetic field, the energy in there is being converted into potential energy in these capacitances. So the line is charging itself. So by the time that it's finished pushing out the current, there is inside these capacitances varying amounts of voltage along that line. Why varying amounts? Because it's been a wave coming out here. So there's varying amounts there. So that voltage, the voltage just there, together with this voltage over there, is forming an oscillation. If you zoom into that oscillation, and I don't have it for this particular one, you will actually find a combination of two waves happening. You'll have one wave oscillating between this inductance here and that capacitance over there, some resonant wave over there. That thing generally, because this capacitance is so very small, this fizzles out very, very quickly. So the resistance of our circuit over here eats up that energy very quickly. Whereas the capacitance of this line and the inductance of this line forms an LC circuit, a resonant circuit, complex resonant circuit that is, because it's not a lumped element as you may think. And it forms that oscillation over there until all the energy has gone. Very important takeaway from this point is this only starts the moment that the EMF over here has stopped and allows the dammed up electricity that we basically have over there and along this line to start moving out again. So that's the takeaway we have over here. I hope you enjoyed this little exercise. I enjoyed it. And the next one I'm going to do, hopefully, I am hoping to test approximately 10 kilometer underground cable consisting of even lower resistance. So I'm trying to get to a situation where the dissipating or the losses in the transmission line is so low that we can see the wave action for a longer period much better, because it doesn't dissipate that quickly. So that project, of course, depends on factors outside of our control. So let's see if we get access to the 10 kilometers of underground cable, and we'll see how that works. Thank you for watching.